You know, right at the very heart of quantum mechanics, there's this concept so incredibly strange that it forced us to literally rewrite the rules of reality. It's a full-blown identity crisis. But not for a person, for the fundamental building blocks of our entire universe.
And it all kicks off with what sounds like a simple question, one that scientists battled over for centuries. What exactly is light? Is it a stream of tiny individual particles, kind of like microscopic bullets? Or is it a continuous spreading wave, like ripples in a pond? The answer, it turns out, is a completely baffling yes.
Now, in our everyday world, those two ideas just don't mix. A particle is a thing. A baseball, for instance. It has a definite location, it follows a clear path. A wave, though, that's a disturbance. It spreads out, it can be in many places at once, and it can interfere with other waves. You just can't be both. Or so we thought. And believe me, this was not a new argument. The debate about what light is one of the oldest in physics, and it pitted some of the greatest minds in history against one another.
If you go all the way back to the 17th century, you had Isaac Newton on one side arguing that light was made of these tiny corpuscles, his word for particles, and on the other side was Christian Huygens, who had a really comprehensive wave theory. For over 100 years, the scientific world was basically split right down the middle, just waiting for that one piece of evidence to settle it.
Then, in 1801, an experiment came along that seemed to do just that, settle the debate once and for all. It was the first huge clue in our quantum mystery, and boy, did it point overwhelmingly towards waves.
This is the famous double-slit experiment, first pulled off by Thomas Young. The setup is really elegant and simple. You shine a light source at a barrier that has two very thin, parallel slits cut into it. And then behind that barrier, you just place a screen to see where the light lands.
So think about it for a second. If light were made of particles, like tiny paintballs, you'd expect to see two bright lines on the screen, right? One for each slit. But that is not what happened, not even close. What appeared instead was a whole series of alternating bright and dark bands, an interference pattern.
This interference pattern is the absolute key. It is something only waves can do. What's happening is the waves of light passing through each slit start to interact. Where their crests line up, they reinforce each other, and you get a bright spot. But where a crest meets a trough, they completely cancel each other out, leaving a dark spot. This was it. Undeniable proof, light is a wave.
So case closed, right? Well, not so fast. Just as the science world was getting comfortable with the wave theory, a totally different experiment came on the scene in the early 20th century, and its results were frankly shocking. This is the photoelectric effect. The basic idea is that when you shine light onto a piece of metal, it can sometimes knock electrons right off the surface. It was actually Albert Einstein's explanation of what was going on here that would eventually win him the Nobel Prize. But here's the crucial, mind-bending detail. A wave's energy is tied to its brightness. So a brighter light should knock out electrons with more energy. But that's not what they saw. The energy of the electrons depended only on the light's frequency, its color, not its brightness. A faint blue light worked perfectly, while the most intense red light imaginable did absolutely nothing. Einstein's brilliant explanation was that light must arrive in these little, self-contained packets of energy, which we now call photons. Think of them as individual energy bullets. To knock an electron out, you need a single photon with enough punch, which means a high enough frequency. And just like that, we had undeniable proof. Light is a particle. So now physics was stuck in a genuine paradox. Light was a wave on Mondays, Wednesdays, and Fridays, and a particle on Tuesdays, Thursdays, and Saturdays. But believe it or not, the story was about to get even stranger. This identity crisis wasn't just for light. So in 1924, a young physicist named Louis de Broglie made this absolutely radical proposal in his PhD thesis. He basically asked, what if this duality isn't some weird quirk of light? What if all matter, including things we are positive are particles, like electrons, what if they also have a wave-like nature? So scientists decided to run the ultimate test. They took electrons, the textbook example of a particle, and they fired them, one by one, at the double slits. At first, the little dots on the screen just looked random. But as they built up over time, the unbelievable happened.
They formed the exact same interference pattern that waves do. Each individual electron seemed to be passing through both slits at the same time. The conclusion was just profound and completely inescapable. This dual nature isn't special to light. It's a fundamental principle of, well, everything in the cosmos. From photons to electrons to entire atoms, everything exists in this bizarre quantum state of being both a particle and a wave simultaneously. Okay, so how can something be two contradictory things at the exact same time? Quantum mechanics doesn't really eliminate the paradox, so much as it provides a framework, a set of rules for living with it. The key idea is called complementarity, and it was proposed by the great Niels Bohr. It says that an object has both particle and wave properties, sure, but you can only ever observe one of them at a time. The very act of measuring which slit an electron goes through, treating it like a particle, forces it to abandon its wave-like behavior entirely.
This trade-off can actually be shown in a really beautiful, concise equation. Just think of D as distinguishability, or its particleness. That's how well you know the particle's path. And V is for visibility, or its waveness. That's the clarity of the interference pattern. And what the equation shows is that they're locked in this constant tug-of-war.
So, for instance, if you put little detectors at the slits to find out which path each electron takes, your particleness, D, goes up to 100%. You have full information. But in doing that, the waveness, V, drops to 0. The interference pattern completely vanishes. And on the flip side, if you get rid of the detectors and don't observe the path, your knowledge of its path, D, drops to 0. And what happens? The wave-like interference pattern comes roaring back in perfect clarity. Your V is at 100%. You can know the path, or you can see the interference. You can never have both at the same time. And this isn't just some abstract philosophical point. This fundamental principle of reality is the very bedrock of quantum theory. And that's the science that has given us lasers, transistors, nuclear energy. Our entire digital world is built on this beautiful, bizarre duality. Which leaves us with one of the most profound and maybe unsettling questions in all of science. If the universe behaves differently depending on whether or not we measure it, what is it really doing when we're not looking? What is the fundamental nature of a reality that seems to wait for an observer before it chooses its own identity?